Hey folks, we're going to discuss a new type of PDF, the chi-square distribution. And the chi-square distribution is different than most PDFs that we've seen thus far. Namely, we've mostly been working with normal distributions, such as the standard normal, the t-distribution. However, the chi-square distribution is not normally distributed and not symmetric. But like the t-distribution, its shape depends on degrees of freedom, which we'll see shortly. But in general, it has a right-skewed shape. And furthermore, the chi-square values are not negative. So contrast that with, say, any t-distribution or standard normal, right? There are negative values to the left of the center there usually. So there's some distinct differences with a chi-square distribution. Here are some examples of the distribution drawn out for a few different degrees of freedoms. And you'll notice that the horizontal axis is very different from what we've seen with standard normal or the t-distribution, where, for instance, often a t value or a standard normal value that is 3 would be considered very far off in the tail here, or similarly -3. But notice that depending on the degrees of freedom here, you can quite easily achieve chi-square values that are upwards of 30 or more. So the chi-square distribution is very different than what we've seen thus far. So why are we looking at a new distribution? Well, it's because we're going to look at new hypothesis tests that cannot utilize the standard normal or the t-distributions, because these are going to apply to categorical data. Now, we saw this in the previous video, that the proportion hypothesis test, we could use the z-distribution there. That's because there was a dichotomous variable in which, as we described in the previous video, those proportions are based off of a binomial variable. Here, our categorical data, at least for today's video, is going to be a variable that has more than 2 categories. So it's not just success, fail, but we'll have multiple categories that need to be kept track of. And in the next video, we will see another application of the chi-square distribution that applies to a different type of data. To demonstrate this new hypothesis test, I would like to just go through an example. This is an example of the goodness of fit test that will utilize the chi-square distribution. Suppose we are conducting a study on habitat preference in bird nesting. A 600-acre study area was selected, and the habitat was characterized into 4 regions. So we've got young seral stage forest, old growth forest, meadow, and riparian. And the number of acres that each of those habitat types occupied in that study area are written there. Furthermore, so they are studying habitat preference in bird nesting. So these researchers sampled 134 nests in this study area. Then they categorized the location or the habitat type that each nest was observed in. So out of those 134 nests, 78 were observed in the young seral stage forest, 30 in the old growth, etc. Okay, so why are we utilizing a new kind of test? Why are we not just using a t-test? To help address that question, let's identify the response variable for the study and what type of variable it is. Okay, so the researchers are observing the habitat in which the nests are observed. So the response variable is the nesting habitat. Right, they're not measuring or counting per se, they are recording the habitat type that the nest was observed in. So the type of variable that this is, that is categorical, right? And furthermore, these categories such as old growth, meadow, riparian, there's no particular order to them. So this is a nominal categorical variable. We will not be able to use a t-test here. We're not measuring averages or standard deviation of our response variable. For the researchers to determine if there is some sort of habitat preference in nesting birds, they need to compare the observed distribution of habitat usage and compare that to the distribution of the habitat. In this example, the null and alternative hypothesis that we are going to establish, well, the null hypothesis is that there is no change, right? Or in this case, that there is no habitat preference, which means that the nests that were observed in their various habitat types, that those nests occur in proportion to the fraction of acreage for each of those habitat types. The way that the null hypothesis is represented for a chi-square test, well, I like to put a brief sentence about what this is stating, but we need to be quite specific. We need to indicate the precise probability of observing each habitat type being used by a nesting bird. And here, because there was 600 acres study area and 408 acres was the young seral stage forest, that gives us about a 68% probability of observing a nest in a young seral stage forest if there was no habitat preference. And so we're going to kind of go down the line here and write out each of these probabilities. And you'll notice I'm just taking the fraction of the acreage for each habitat type and dividing it by the total acreage. Of course, these need to add up to 1. So this is saying that if there truly was no habitat preference, we would expect to see 68% of nests in the young seral stage forest and 5% of nests in the riparian zone, etc. So this is the distribution of expected proportions of habitat usage under the null hypothesis that there's no preference. So the null hypothesis needs to be pretty specific. However, the alternative hypothesis is usually just a brief statement, which contrasts the alternative, which indicates in this example that there is a habitat preference among nesting birds. Next up, we need to start getting ready to create the test statistic. To do that, we need to compare our observed data to what is expected under the null hypothesis. So here, these are the expected number of times the habitat is used if the null hypothesis was true. We need to remember the ultra brief formula for the expected value. Remember, that's just n times p. Here, we remember from a moment ago, click rewind, that the sample size was 134. And so how many nests would we expect to see in each of these habitat types, assuming these probabilities? So I'm just going to multiply our sample size by each of these proportions written above. Now, some of these are going to result in decimal values. That is okay. Just keep those. So these expected values indicate the number of times that we would have observed these habitat types for the nesting birds if there truly was no preference. Now up above, we have the actual data of what was actually observed. We're going to compare the observed data that's above to these expected values in the test statistic. The test statistic for a chi-square goodness of fit test. So I have the chi-square symbol written, S, because this is a test statistic from sample data. And it is the sum of the observed values from the data set for each category minus the expected value for each category, which we just computed. Those differences are squared, so there's a direct comparison between what was observed in the data, what was expected under the null hypothesis. And then this is divided by the expected again. Let's see this pan out for this example. We'll start with the young seral stage forest, and if you rewind, you'll see that there were 78 nests observed in that habitat type. However, 91.12 were expected. We will square that difference and divide by 91.12. We will now add the next term here. Old growth forest was observed for 30 nests. However, if there was no preference, we would have only expected 28.14. Again, subtract, square, divide. Meadow is next. And lastly, the riparian zone. This one appears to have a pretty big difference. I'm going to actually write out what some of these terms come out to, because that's going to be a value in a few moments. So our chi-square test statistic, about 28.93. This test statistic was the result of these four values added up. These terms, there's four terms here, are called chi-square contributions to the test statistic, and more on that in a few moments. Let's continue on with this hypothesis test. As usual, the next step in our hypothesis testing world is to determine the p-value so that we can state a conclusion to the hypothesis test. With the t-test, we've often drawn an image to help illustrate the probabilities that we are finding for a p-value. I would like to do that here as well. Kind of a quick drawing of a chi-square distribution, and we need to say what the degrees of freedom is here. Well, for a chi-square test, the degrees of freedom is actually, it's not n minus 1, it's k minus 1, where k is the number of categories. In this case, because there were 4 habitat types, 1, 2, 3, 4, here our degrees of freedom is going to be 3. So that is going to be denoted here. Our test statistic, remember this distribution is very different looking and has very different tick mark values. 28.9 is going to be pretty far off in the tails. 28.931. Regardless, the p-value is always the probability of observing results that you observe in your sample or something more extreme. So it would be this tail region down here. That's our p-value that we need for this test. Now there's no doubling that's going to occur here because there's not a symmetry occurring with this distribution. So how do we find this p-value? We're going to use R. We need a probability that corresponds to the chi-square distribution. We will see more details of these functions during our lab session. However, the distribution is chi-square, CHISQ. Because we want a probability, we need to put the letter P in front, not the letter Q. So P chi-square, our chi-square value was 28.931, and the degrees of freedom was 3. Because we want the area to the right, we need to use the complement, 1 minus P chi-square. And our p-value is incredibly small. It is definitely smaller than any reasonable level of significance. Now that we have our p-value, we are ready to state a conclusion to our goodness of fit test. As we can see, this very, very small p-value is going to be less than any reasonable level of significance using the good old 5% level of significance indicates that our data provides sufficient evidence, possibly even strong evidence, to reject the null hypothesis. As always, I like to provide an interpretation to this conclusion. Yes, we are rejecting the null hypothesis, but what does that imply about the nesting habitat? I copy-pasted our hypotheses here, kind of small. Because we are rejecting the null hypothesis, that means that the evidence is in support for the alternative. Therefore, as brief as I can state this would be that the evidence suggests the statement in the alternative that there is a habitat preference among these nesting birds. Remember, we do not prove that there's a habitat preference. This is just what the data seems to be in support of. Right? This could be a type 1 error, but we don't know. Okay, I have a couple supplementary questions to ask. Which habitat type shows the largest relative deviation from the expected habitat usage? And which direction is that deviation? Okay, so this is where the chi-square contributions come into play. So we're going to go check those out. So looking at the test statistic here, these 4 terms are each considered chi-square contributions because you added them up and that got you the test statistic. each of these terms essentially is an indication of the relative deviation of the observed and expected habitat usage. This is essentially what every test statistic does. Here we can kind of track it down per category. The values of these contributions, notice one of them is much, much bigger than all the rest. This is the category of the riparian usage, where the riparian habitat was used much, much more than was expected. Only 6.7 nests were expected to be observed in the riparian zone if there was no preference in habitat use. But 20 were observed there. So that is a big relative deviation. So therefore, the riparian category had the largest relative deviation since the chi-square contribution for that category was the largest. So I'm writing here that the riparian habitat showed the largest relative deviation, and that deviation was that we observed much more or higher than expected. And maybe it's worth writing down those numbers here just so it's clear to us. We observed 20, but only expected 6.7. Lastly, there are requirements for all of our hypothesis tests, and for the goodness of fit test here, the requirement is that all the expected values are at least 5 for all the categories, and that, of course, there's random sampling in order for us to have that inferential capacity. So this is a requirement that involves the expected value. So it's not really something you can check off before you start going through the motions with this test. But if we scroll up here, we will see these expected values were all bigger than 5, so that met the requirement. While we're here, I would like to demonstrate how we would do this test in R. More details will be provided during the lab session, but I thought that would be valuable right now. So doing this in R, I've got my previous p-value calculation here, and we can see it in the screen back here, just so we know that we're going to replicate some of these numbers, including the test statistic. I've uploaded the data in a data frame called Nest. So I've got the categories, the acreage that each of those habitats occupies, and the observed number of times that the habitat was observed for all those 134 nests. Remember that we needed to compare these observed values to the distribution of the habitat, where under the null hypothesis, the habitat is used in proportion to its fraction of total acreage. So I'm going to make a fraction of the acreage here. And this is under the null hypothesis that the use of the habitat is in proportion. So I just need the acreage as a fraction of the total acreage, and that's not going to work because I need to do nest $. And if we take a look at the null acreage vector here, those are the same proportions that we had in our null hypothesis. Feel free to click rewind to check that. The way that this is typed for the chi-square test, it is chi-square dot test. The first input is our observed values, so I will do nest $observed and there's a comma. The second input requires p equals, and this is where we will put that vector of the fraction that each habitat takes up. Now when I run this, again, we should see our test statistic and this p-value come to life. Here is the test statistic, chi-squared. The degrees of freedom, remember, is based on the number of categories, k minus 1, so that's a 3. And lastly, our p-value, recall it was a very minuscule amount, and there it is right there. And if I scroll up, strategically scrolled up here, here was our calculation using p chi-square for the p-value outside of the chi-square test function in R. I would like to demonstrate one more thing with this chi-square test in R. Is there's a lot of calculations that go on in the background. Here we were only given a certain number of outputs, such as the p-value, the test statistic, but you can access those background calculations if you know what to type by asking R at the end of our chi-square test input. If I just go $expected, it's going to output our expected values. Those hopefully look familiar. I think I can get them displayed there. Indeed. I could even use R to determine those chi-square contributions. I'm going to need these expected values, but I don't want to type all this every single time. So I'm going to call this nest expect. And now I've got these 4 expected values in a much smaller vector. And we know what the observed values are. So nest observed, if I subtract the expected from the observed amounts, square that difference, and then divide by the expected, this should get me our chi-square contributions. Oh, and I wrote expected instead of expect. We all make mistakes. And there they are, 188.12, etc. So you can do this whole process in R. Well, that'll be the end of the day for this video. I hope you found it useful.